Okay, Bismillahirrahmanirrahim. So let's start this lecture. This lecture is about the design of springs. So today we will see some numerical problem for the topic of helical spring, and also we will go through the some theory behind the leaf springs, and also we will be able to solve one or two examples related to leaf springs. So in the class we have gone through the theory of the design of helical springs, and we have understood the relations, how relations has been developed, and how to use it. uh, what are different parameters that are involved in the designing of the helical springs. So just to have a quick reminder of what we have done in the class. So let's say in the class we have actually touched the topic of the helical springs. And you know from your previous understanding, the helical springs are the spring that looks like a helix. We have different design parameters like the wire diameter, like the mean diameter, the spring index of the spring, and in some cases the K as well. These are some design parameters related to the helical springs. So in the class we have solved some problems like we have actually gone through certain relationships. The first relation is tau is equals to 8fd over pi d cube, and there is a multiplication of a stress factor. So this is one factor we call as stress. This is normally known as the shear stress factor. Shear stress factor. Whereas there is another relation when we have applied the wall correction factor in the same relationship, and that is 8fd over pi d cube, and that is I think that is 4c minus 1 divided by 4c minus 4 plus 0.615 divided by c. So that is we call as wall factor, or sometimes called as wall stress factor or wall correction factor. So in the exams, if it is written that ignoring the curvature effect, so if written that ignore the curvature effect, as we have studied in the class, that the wall correction factor is actually applied because the curvature effect is introduced when we actually springs are made from a straight wires. So when they are coiled in a helix shape, there is additional stress due to curvature, and that actually increases the shear stress in the spring, and the factor that actually compensates is called wall correction factor. So if in the exam it is written ignore the curvature effect, so you have to use this relation for the shear stress. But if in exam is written that consider the curvature effect, consider the curvature effect. So in that particular case you have to use this relation, which is 8fd pi d cube into 4c minus 1 over 4c minus 4 divided by plus 0.615 divided by c. The another relation we have gone through the class, that is we have actually derived this formula that is called deflection in helical spring, that is 8fd cube n divided by d4g, where capital N are the number of turns, and more specific number of active turns, which means there are two turns in the spring on the either side which has been grounded. Generally mean they have become grinded to a flat so that they can rest on a flat surface or a flat plate. So the number of active turns means those number of turns which are, let's say if you look at springles, so normally the last helix is, or last turn is rounded. So generally these two turns are not considered as the active turns. Only the number of turns that is in between these two inactive turns are considered as the active turns. So n is generally recognized as the number of active turns. whereas G is the modulus rigidity of the spring material. Whereas K is also can be derived from the Y relation by F is equals to, sorry, K is equals to F over Y, and you get 8 at over 4D D4G divided by 8 D cube N. So these are certain relations that we will going to be used in our problems. So we have solved some problem in the exams, but for a quick revision, let's start with a new problem, and I'll just first show you the just give me, that is, I think, so example 3. Yes, so we have done this problem in the class, but just take a revision, I'm just solving it here. So this problem says design a helical spring. So there is a spring for a balance. Now you have seen the spring balance, I think, in your childhood, where there is a small casing. The casing is sometime like this, if you remember, and we have a casing like this, and there is a spring in between, and there is a hook. Clear? So there is a ring over here, and there is a scale marking on this. One scale on this side and one on this side. Clear? So one side the scale is kg, the other side is Newton. And when you hook a load, any weight on this, it actually there is a pin attached to this. There is a pin attached like this, and this pin actually moves downward because the load, and then we can see what is the actually load that is hung through the spring balance. So this is the spring we are going to design. This is the spring that actually gives you the weight of the whatever the weight is hung from that hook. So it says it has a scale from 0 to 1000 Newton. As he has told you that it has on the one side a scale of kg, the other side has a scale of Newton. So it's ranging from 0 to 1000. Clear? Over a scale of 80 meter, which means that the length in which there is scaling is actually 80 millimeter, which means that spring can deflect. The total deflection of spring can be, so generally, if I will be more precise with respect to this drawing, for example, to be more precise, so what happens is that you have a spring that is coiled like this, and there is a hook here, pin here, and that is set as 0. As soon as you apply, and there is a small hook over here, so spring deflection here is 0. So pin marked as 0 and 0 location on both scales. As you apply a load, the spring becomes stretches, and due to stretch, this pin actually goes downward. So the spring can deflect by a distance of 80 millimeter. So the spring is to be enclosed in a casing of 20 mm diameter. So the width of this casing is 25 mm, and which spring has to be enclosed. Number of turns, approximate number of turns 30. The modulus rigidity is 85 kilonewton per millimeter square. Always remember this 85 Newton per kilonewton is gigapascal. So you can also say that it's 85 gigapascal or 85 kilonewton per millimeter square, as you know. So you have to find two things. One is design. Design generally means you have to find small d, you have to find capital D, and you have to find C. Clear? You have n is also number of turns, also design parameter, but in this particular problem the n is given. Clear? So, and the last thing is the deflection. Sorry, not deflection, stress. The total stress induced. So you have to also find the stress here. Now, there are two ways to solve this problem. I just explained both of this in this lecture. So now we don't know all these parameters. Let's start with the deflection formula. So deflection formula, as we know, is 8f d cube n over d4g. Now we know from this relation neither capital D is known nor small d is known. Clear? Now from the theory, we know that when coil is made, they actually have a wire. Clear? This wire has a diameter of d, and the distance from the center of one wire to the center of other wire is normally known as mean diameter, whereas the outer diameter is generally referred to as d naught. So you can say the capital D is d naught, which is the outer diameter, minus small d. Small d, why? Because it is taken from center to the center. So we have a 1 d by 2 here, radius here, and 1 by d2 here. So if we subtract the d from the, d means d by 2 plus d by 2. So d is d by 2 from one side and d by 2 from other side, from this side. Because again I am repeating, the d is taken from the center of one coil to the center of other coil. So the one radius is left over the left side and one radius is left over the right side. So if you subtract the whole diameter, or you, in the terms you can say minus d by 2 minus d by 2, which is actually equals to d. So you end up with the mean diameter, which is, by the way, is the design parameter of the spring. So you can see in this formula, now d outer is what the maximum outer diameter of spring. Clear? Now there are two ways to solve it. The one way, the simplest way is, so let's say I have the casing. I have to enclose a spring with the casing diameter is 25 mm. So I have to take a spring which does not touch the sides of the spring, but at least a slightly smaller than the diameter in which the spring has to be enclosed. So let I take capital D is 24 mm. Now someone can argue that why 24, why not 23, why not 22, why not any other value? Now, but we do not want spring to be much smaller than the casing. But we do not also want that if the diameter of the spring is equal to the diameter of casing, so spring when moving along in this casing will generate some friction by sliding through the walls, and that actually causes an error in the measurements. So let's assume that the diameter of spring is slightly smaller, which is about 1 mm smaller than the casing. This ensures that the spring is not much smaller. Again, the small spring do not carry this much. That's a load of 1000 Newton, which is roughly about roughly 104 or 105 kg. So you do not want this to be much smaller, but at least smaller to a scale where it does not touches the casing of the spring in which it has to be enclosed. So let's say take it D is equals to D outer, is equals to 24 mm. So capital D is written as 24 minus small d. See, relation is given. Now again go back to the relation of y. So y is 8f d cube n over d4 g. Now I can now replace in this, I can replace capital D by this relation. Clear? So just write y is equals to 8f 24 minus d whole cube n divided by d4g. If I start putting the values, y is 80 millimeter, which is written as 80 Newton to the power minus 3. I'm converting all these into meters. F is actually 1000 Newton, because the maximum load that we are going to carry, the spring is going to carry, is 1000 Newton into this d is not known. Number of turns from the relation is approximately 30. So just multiply it by 30 divided by d4, d is not known, just right here, and g is the molar rigidity of the spring material, which is 85 kilonewton per millimeter square, or 85 gigapascal, which is 10 to the power 9. If I take these two terms here, if I keep these two terms here and take all things on the left hand side, So 24 minus d whole cube divided by d4 is equals to, we just have to use calculator for that to find the values. So it's 80 exponent minus 3 into 85 exponent 9 divided by 8 into 1000 into 30. Eight into thousand. Sorry. It's 18 to the power minus 3. I just do calculations again. So 80 exponent minus 3, which is the deflection. And just check what is the deflection. So deflection is 80 mm. Okay. So 80 exponent minus 3 into 85 exponent 9 divided by 8 into 1000 into 30. So value will come out to be 28,333.3. If I take a cube root of it, so in order to remove this cube, I take a cube root, and that becomes 24 minus d divided by d power 4 by 3. And if I take a cube root of this factor, if I take 28,333.3 power 0.33, so that value will come out to be 29, or just hold on, 28333.3, and that is 28333.3 power is 0.333, is approximately 30.46. Clear? Now from this formula we intend to find d. So 24 minus d is equals to 30.46 into d power 4 by 3. So we'll just check it again. Just I'm recalculating it so that there should be no error. It seems that there might be some error in calculation, so I just have to do it again. 8 into 1000, 80 millimeter, which is 80 into exponent minus 3. Okay, into 85 gigapascal, which is 85 exponent 9 divided by 8 into 1000 into number of turns are 30. Okay, that is sorry, that is 2666.7. I'm sorry, there has been some error in the calculations. So just take a cube root of that value, power 0.333. We take a cube root. There might be I'm getting some error in the calculations. So 8 fd cube n over d4g. So capital mean diameter is 24 minus small d, where 24 is outer diameter and d is the wire diameter. I'll just do it again because I'm have a feeling that I'm getting some error calculations. So 80 mm is 0.08 into 85 exponent 9. So if I take a cube root 28333.3, that is 29.46. So that value is 29.46. So 24 minus d is equals to 29.46 d power 4 by 3. So if I take this value, I'm not understanding, I'm still getting some error. Actually there is error in one of the decimal place. So this is, I am trying to figuring it out where actually this is going wrong. There might be a problem in the units, probably. I don't know yet. Because this actually has a one decimal place more than what I thought it should have been. So let's check another. Let's check it again. So deflection is 80 millimeter, which is 8 centimeter. That is oh yes, yes, yes. Sorry. That must be because that I'm oh, yes, I'm actually got the point. The all of the units are in meters. I'm using this in millimeter. This must be 0.024. Oh, I'm getting it. Okay, so that is 0.024. You can also use in millimeters, but I'm going in meters. So I've actually got the fault. So that is actually equals to 0.024 rather than so it's 24 millimeter. So what I get is 0.024D is equals to 29.46 D4. So you can now say that 29 point you can now say that 29.46 d power 4 by 3 plus d is equals to 0.024. Now in your calculators you can actually use calculator to solve this equation and you get a value of d for it. So but generally I just give you a general hint, if I am unable to solve from calculator, you have a general idea that d, which is a wire diameter, generally the springs that are made from these wires, the wire diameter actually varies from 1 to 10 millimeter. Generally, not in all cases, generally it varies from 1 to 10. So what you can do in your exams, that if you are able to solve this in your calculator directly, it's good. But you're unable to do it, just use hit and trial. So for example, let's say I use first value of, let's say, 3, for example. Put d is equal to 3. So let's start with the value of 3. So you can now say 29.46 into at 3 millimeter again. So that will be 0.003 power 4 by 3 plus 0.003. So let's say if I come out with the answer of 0.024, let's see. So 0.003 power 1.33, which is 4 by 3, plus 0.003. So I am getting a value of 0.0034. Clear? Now this value is actually seems to be larger than this. Okay, if I take a value of d is equals to 4 millimeter or 0.004 meter, so 29.46 into 0.004 power 4 by 3 plus 0.004. Let's see what is the answer. So 29.46 into 0.004, okay, that might be wrong because I actually do not use a BODMAS rule for that. So let's start with the point with the 4. So 0.004 power 1.33 into 29.46 plus 0.004. See, I am getting a value of 0.0023. which is very close to 0.0, sorry, not 0.00, it's 0.02, sorry, 231. So see, this value is very close to 0.024. In exam, there is no need to find the exact value, but when you use the closed value, so I can say D is approximately equals to 0.004 meter or 4 millimeter. Just to put a value of 3 again. So this is there is some error. There is some error in the calculation. Just putting the value of 3 again. So that comes out to be 0.003 power 1.33 0.003 power 1.33 into 29.46 plus 0.003. So we're getting a value of, we have a value of approximately 0.016. See, this is very small. So when you get a value of 0.4, yes, its value should be slightly larger than 4. Just take a value of 5, for example. If I put D is equals to 5, so what will happen? 29.46 into 0.005 power 4 by 3 plus 0.005. Again, I am repeating, we are using the units in meters. If you are not comfortable in meters, just do all these calculations in millimeters. Clear? So then you have to take it as 24. So that's why, just to be clear in your mind, that there should be one system of units. You have seen the problem that even I have actually got some fault in calculation. So that's why it's very important to first understand the units and then try to solve it. So if I take the value of 5, for example, so just use it, 0.05 power 1.33 into 29.46, sorry, 0.005 power 1.33 into 29.46 plus 0.005. So you get a value of approximately 0.03. So this value becomes larger than 0.024. So see, now you can easily understand the value is close to. So now if we know the wire diameter, which is 4 mm. Now you can also find the mean diameter, which is 24 minus small d, and that is 24 minus 4, which is 20 mm. Another parameter required can be C. So C is 20. C is actually the mean diameter over wire diameter. That is capital D by small d, and that is 20 divided by 4, and which is 5. Clear? So this is what is required from this problem. The design contain actually these three important parameters. The last thing is the shear stress, maximum shear stress. The maximum shear stress means the maximum shear stress actually can be calculated from the wall factor. So higher stress will be calculated if we use the wall factor. So although in the problem it is not written that either you have to take the curvature effect or ignore the curvature effect, but in the problem it is written find the maximum shear stress, and in this case we have to do wall correction factor. So we know all these values. So 8 into 1000, again I will use the meter unit. So D will be 0.024 divided by pi into D is 4 millimeter, which is 0.004 power cube. Now spring index is 5. Now again for the check you have to see that C must vary from 3 to 21. If in some problem your spring index, which is C, is either less than 3 or greater than 21, it means your problem is wrong. Your solution is wrong. The problem will be right, because in the exam when we are given a problem, we will first solve the problem and then we'll give you in the exam. So always check for C, that if your C lie between 3 and 21, it means it's right. If it is does not lie in this range, then there's probably some fault in your solution. This is just for a check. So 4 into 5 minus 1, 4 into 5 minus 4 plus 0.615 divided by 5. So if I calculate this, so 8 into 1000 into 0.024 divided by pi into 0.004, and the power is cube. So that come out to be, I'm just writing it here, 954 929 658.5, and let's try to find the wall correction factor, and that is 20 minus 1 divided by the 20 minus 4, which is 16. Sorry, it's 19 divided by 16 plus 0.615 divided by 5. So that value come out to be 1.31. Clear? So if I multiply 1.31 with a very long value, which is 954 929 658.5, so that value will come out to be 1250 957 852.6 Pascal. So if I just move this this to convert into megapascal, so 1 2 3 4 5 6, so your stress will approximately equals to 1250.9 megapascal. You see, this is a very high stress. So for the springs like this, the stress normally should range from 300, 350 or 400 at most, but this is a very high stress. Now this certainly indicates that either your spring is very small for this much load. So for, let's say, for a load of 1000 Newton, which is approximately about 100 and 104 kg, the spring of 24 mm diameter is a small spring. So what you have, because stress actually tells you it's a very high value. So one way of actually re-evaluating or recalculating the spring or redesigning the spring is try to take a larger spring which has a slightly larger diameter, so that the stress induced in this spring because of the load of, let's say, 1000 Newton must be smaller and does not fail the spring. The another way of solving the same problem is again using the same formula, that is 8f d cube n over d4g. Now if we know that c is equals to capital D by small d, and so if I just write this formula like this, 8f, and it just I take d cube over in the numerator and only remain d in the denominator, so that will come out to be y is equals to 8f into c cube n over dg. If I put the values, 18 to the power minus 3 equals to 8 into 1000 into c is not known, n is 30 divided by d is not known, and g is 85 into 10 to the power 9. So I can find the value of d cube over d, which is 28.3. Sorry, just solve it. Just one minute. Okay, so C cube over D is 0.08 into 85 exponent 9 divided by 8 into 1000 into 30. So C cube over D is 28333.3. Now this is the formula. Now there are two ways to do it. One is assume any diameter, y diameter of spring, and then check whether your mean diameter, which we know from the formula, is where D outer must be less than 25 mm. When you calculate your D outer, that must be less than 25 mm. So one way of doing this problem is, if rather using a previous approach, which is developing an equation for D, a very complicated equation, and then use an inter-trial method or the equation solver method, try to find the y diameter. We assume a y diameter. Clear? So let's say again assume here 4 mm. Now you can also argue here that why 4 mm, or as a problem we have actually solved with the previous method, so we don't know in the exam. So even in the exam we have to do the same thing. The assumption is actually again take it from 1 to 10 mm. Take this value on your own and just check your outer diameter must not be larger than 25. If it becomes larger than 25, take another value. So if I take this value, so y diameter of 4 mm, so C cube will be 28333.3. Your y diameter is taken as 4 mm, so into 0.004. That value will come out to be 113.33. So your C will come out to be, if I take a cube root of this, it becomes 4.76. Again check the C, that range between 3 and 21, and in this case works fine. So okay, no problem. Let's go. If C is this, we know that C is capital D. C is capital D by small d. Now we know what D is, we know C is, so capital D is C times small d, which is 4.76 times 4. 4.76 into 4, which is 19.04 mm. So outer diameter, we know from this formula that outer diameter from here will be D plus small d. So capital D plus small d. If you add these two, the mean diameter and y diameter, you get the outer diameter. And see, this is the outer diameter is 19.04 and the y diameter is 4, sorry, plus. So that is 23.04 mm. Now see, that also works fine. It should not be much smaller, like if you take d is equal to 3, you still get a smaller value. But do not go very small value like 18 or 19, go around 20, between 20 and 25. So in this case 23. So outer diameter is fine. This is another way of solving the same problem. In the exam, it's your choice to use whatever method you want, but keep in mind that the check is very important, which means the outer diameter must be less than 25 mm. This is what the desired condition, and the rest is the same. We have to find the stress again. So there are two ways I have solved it. I just actually shown you the two methods of solving it. I hope you understand the problem from do perspective. Sorry, from the start I've actually stuck with the units, so it takes more time than I anticipated. So let's start with the other problem from your lecture notes or lecture slides. So let's see with the example. Okay, just to give you an idea, now you know the complicated problem. Now these problems are relatively simpler. So you have to design a helical compression spring. The load is 1000 Newton. The deflection is 25 mm, and the spring index value is 5. So you have to design it. We have to find the wire diameter, you have to find the coil diameter. So we already known. The tau is given, maximum shear stress, which is 420 megapascal, and your G is given, which is 84 gigapascal or 84 kilonewton per millimeter square. It's the same. Okay, you have to design a spring. So which means that you have to now which formula you can use. So see, the deflection is known. So okay, which means that C is capital D by small d. So capital D by small d is equals to 5. So you know that capital D is 5 times the small d. Clear? If I take the stress formula, and in this case, if it is not specified in your problem that either you have to use shear stress factor or the wall factor, to just use the wall factor. If it is not given in the problem, neither there is any indication of a curvature effect, nor it is like in this problem, there is no indication of whether to use a shear stress factor or a wall correction factor. So just use the wall correction factor formula. So I'm just using here 8fd over pi d cube into 4c minus 1 over 4c minus 4 plus 0.615 divided by c. Clear? So now, and here you have to put tau allowable. Whenever you're designing this the spring, just use tau allowable. So that will be equals to, now in this case, replace capital D by this formula. So tau allowable, I'm putting all the units in the SI units, all these parameters in SI units. So it's 420 into 10 to the power 6, 8 into F is 1000. Now D is written as 5 times small d divided by pi into d cube, where this will become cancelled with this, and this is 4 into 5 minus 1 over 4 into 5 minus 4 plus 0.615 divided by 4, so 5. Clear? So if you solve this, and you just take d here, just solve it. I'm just writing a direct value, you can also solve it. So d will approximately come out to be 0.0063 meters, okay, or 6.3 millimeters. So see, again, this value actually ranges from 1 to 10. So generally wire diameter generally varies from 1 to 10. Clear? So if C is known, if small d is known, then you also find the capital D, which is 5 times the wire diameter. So 5 times 6.3 is approximately 31.5 millimeter. Clear? Now I've told you, whenever design also have a number of turns too. If number of turns are given, then 5. If number of turns are not given, you have to find the number of turns. So number of turns are usually find from the deflection formula, because only in the deflection formula number of turns are indicated. So y is equals to 8f d cube n over d4g. So n can be written as y d4g divided by 8f d cube. So y in this case is 25 mm, which is 25 into 10 to the power minus 3. Small diameter, wire diameter is 6.3 millimeter. which is 6.3 into 10 to the power minus 4 power 4, minus 3, minus 3 power 4. G is 84 into 10 to the power 9 divided by 8 into 1000 into the wire diameter is 31.5. 31.5 into 10 to the power minus 3 power 3. So number of turns will come out to be approximately 30 is nearly 14. The exact value, I'll just calculate the exact value for you. So the exact value will come out to be from this relation. Okay, just find the direct value. So 0.025, which is 25 to the power minus 3 into 0.0063 power 4 into 84 exponent into 10 to the power 9 divided by 0.315 power 3 into 8 into 1000. So its n is equals to 13.23. Approximate you can take it as 14. So number of turns must be 14 for this spring. So see, we've actually evaluated all the values. So yes, there are two other factors. There are two other factors. In the design, you have to find all these factors. So next design factor is total number of turns. Total number of turns. Total number of turns is generally the 14 active turns plus 2 inactive turns. If you can also consider it as a square grounded ends. So it's a problem which is not given that what are the end conditions for the spring. Generally 2 ends are squared. Squared means generally spring have a round shape, round outer surface, but if you want to rest it on a flat plate, the contact area is small, which induces the high stress. So we just grind this stress in such a way that its contact area becomes larger, so it becomes squared. Its shape becomes squared when it rests on the plates. This has two end coils. So 2 inactive, total number of turns are 16. So the number of turns 16. The next term is the total length of spring, and that is again very important. Total length of spring, and that is equals to number of turns. Okay, number of turns into wire diameter clear, number of turns, and but that equals to a solid length of spring, which means if a spring is like this, and if I just they become clashed together such that there is no space between these two, so that will equal to number of turns times the diameter of wire. So one wire has a 1 diameter, so solid length of the spring is number of turns times the wire diameter plus the deflection, and that deflection is the maximum deflection allowed in the spring. Clear? So this is the solid length, n times d, plus generally we take 15% of clash clearance, which means that the spring, when spring is fully compressed, there must be at least 15% of the total space left between the coils. So coils do not clash between together. I'm again repeating, for the operation of a spring, we generally want that whenever spring is fully compressed, it has at least the 0.51% of clearance of the total deflection. So that is so if I just find adding all these will give you a total number of springs. So N is 16. The wire diameter is 6.3. This is the solid length plus the deflection. Like deflection in this case is 25 plus the clash clearance, which is 0.15 or 15% of 25. If I calculate this value, (16 into 6.3), that is 100.8. So 100.8 plus 25, and 0.15 into 25 is 3.8 plus 3.8. So 100.8 plus 25 plus 3.8. So 129.6 mm. So whenever you design a spring, that spring has a total length of at least, it could be larger than this. This clash clearance is the least clearance. Sometimes you want that this clearance must be 30%. You can also do that. This is the least value. So this indicates that spring has at least the length of 129.6 millimeter, which is roughly about the 1.3 meters. Okay, about 12 centimeter. Clear? So you have to now imagine that if this length can fit in your assembly or not. This is again a very important concept while designing a spring. Clear? So this is what actually we want. The last of the design parameter is called pitch of spring. Pitch of spring. And pitch of a spring is, if this is the spring, the distance between two successive coils is called the pitch of the spring. This is again very important. Why? Because we also want to know what is the distance between, and that is very simple. And that is free length, or we generally call as L. So pitch is free length. We calculate it as L, total length or the total free length of a spring, divided by number of turns, total number of turns. Just write here N prime, which is total number of turns, minus 1. Yeah. So pitches and minus 1 means we actually exclude these the end coils, because they are actually grounded, so their pitch does not actually is the same as with the other springs. So we just minus 1, total number of turns minus 1. So this is 129.6 divided by 16 minus 1. So that is approximately equals to 8.7 millimeter. Clear? So again, if it's problem design a complete spring, you have to find small d, you have to find capital D, you have to find C, you have to find number of turns, you have to find total length, and you find the pitch of the spring. These are all the design parameters. If you design the whole spring, so in the exam, just keep in mind there is a possibility that all of these parameters cannot be found. But I think in most of the cases you can find it. Like the number of turns, I've also given you the total length formula, which will remain same for all the springs. The total number of turns you can consider square and grounded ends for all springs. Clear? So in this particular case, you have to add two more turns, one on the upper side, one on the lower side. These are called the inactive turns. These turns are provided in order to provide a flat resting surface on the upper plate and the lower plate, in which generally where the spring has to be mounted. The other spring, like these formulas will be given, but you need to understand these are all the design parameters for a spring. Now, just for the case of the better understanding and the more comprehension about the topic, I just will able to solve today one of the little bit more practical problem, and you will understand from this problem that this is, by the way, the problem from the one exam that I have taken, and this will give you a very comprehension of how the problem will be given in your exams. So if you look at this problem actually is a problem of a clutch plate. Now if you look at the clutch plate, this is the clutch plate of a car or any small vehicle like Mera or Alto. This is, by the way, the actual picture of a Corolla clutch plate. This actually has 5 helical springs, as you can see here. These are the 5 helical springs. Clear? And this black surface is the surface which actually provide contact between gearbox and your wheels. So when you press the clutch, this clutch plate disengages the gearbox with your engine. So you can shift the gear, and as you release your clutch, this actually provides a contact between your engine and your gearbox, where gearbox directly actually transmit your power to your engine, so to your car wheels. So there are different number of springs in the clutch plate, like in the clutch plate of a trucks there could be more than probably about 6 or 7 or 8 springs. In generally in car there is 4 to 5 springs. Now in this particular problem, so I just read the problem for you. An automobile single clutch plate consists of a two pair of frictional surfaces. So we have, this is called frictional surface. Two pairs means one on the this side, one on the other side. One between the friction lining and the pressure plate, another between friction lining and the flywheel. So we have the flywheel on the one side, the pressure plate on the other side. So we have a whole assembly of it. We have a diaphragm spring, we have pressure plate, and then we have a clutch plate. If you want more detail of this, go Google it. You will find the clutch plate assembly, which is pressure plate, clutch plate, and diaphragm spring. So in order to, we are not talking about diaphragm spring because they are different kind of spring. We are talking about this helical spring which are provided. By the way, the function of these helical springs is when there is a contact between the gearbox and the engine, there is a jerk or there is a sudden load because it start rotating. These springs actually bear that load. And not only this, they provide because the clutch plate is continuously rotating, they actually are experiencing the load all the times. So 5 identical helical spring, as you can see in the picture, made from ASTM A229. This is one of the most popular use material for these springs, arranged in parallel. So because these two are not joined directly, so they all are in the parallel arrangement. Provide flexibility in the system. This flexibility important because to provide shocks. If there's no flexibility, whenever there's a sudden engagement or disengagement of the engine and the gearbox, there might be a damage in this clutch plate. So generally, if someone who experienced with by driving the car, this clutch plate rarely will be wear out because of these springs. These springs actually provide a flexible contact which actually absorb most of the shocks while actually changing a gear to disengage between engine and the gearbox. So see, the total force experienced by all the spring is 24 kilonewton, and the corresponding deflection of each spring is 0.9 mm with a total clash clearance of 6 mm. Clear? So the total clearance, the total deflection is 0.9 mm, where the total clash clearance after it has gone to a maximum deflection is 6 millimeter. The outer diameter of a spring should not exceed 25 millimeter. Why? Because you can see housing here. So there is a housing in which this spring has to be rest. So this must not be larger than 18 mm. Clear? So just give me a minute. Okay, so you have to design a spring. Okay, now it is written analyze the spring and condition known spring square grounded, analyze and design the spring keeping in mind the curvature effect. Now it is clearly mentioned that you have to consider a curvature effect. So yield stress of the ASTM 229 is given, modulus rigidity is also given, and the factor of safety is also given. Now we have to start designing the spring. Now again remember you to find the wire diameter, the coil diameter, the index, the number of turns. Clear? The don't look at the picture. There are probably 5 number of turns, but this is not the actual problem. So the number of turns can be different from the picture. So don't count the number from the picture. Clear? And the free length and the pitch. Clear? So now let's first start with the, we have 5 springs. So the total load is, so total force on the spring, total on all the springs is 24 kilonewton. And because they are not directly connected, always remember if springs are directly connected, there are series connection. But if like we have a one plate here and this solid plate and then spring are connected, so this solid plate does not, if it does not move, like in this case these supports cannot move. So this is a parallel combination. Always remember, if your attachment point can move, like in this case, if this spring moves, this attachment point also moves, then it's a parallel series contact. But if you have in between those springs a strong contact which cannot move, that is a parallel combination. Why I'm saying parallel? Because parallel, the force, the total stiffness is the sum of all the stiffness, and the load carried by each spring, if we call it Fs, it is 24 by 5, which is 24 by 5, which is 4.8 kilonewton. So it's a parallel. Every spring will experience the equal amount of force, which is 4.8 kilonewton. Clear? So this is the first point, the most important point. In many cases in the exam, even in the exam, there could be more than one number of springs. So you first have to see how many springs are carrying the total load. Another consideration is D is equals to, and we know from previous understanding that D is equals to D naught minus D. So mean diameter is, and the outer diameter does not exceed 25 megapascal, which means that now it is does not written, it must be less than 25. If it is written in the problem that it is less than 25, take it 24. Now in the problem it is written the outer diameter should not exceed. Exceed means you can still take a value of 25. Remember, minus D. And because again we got confused into units, so please write here 0.025 minus D. Clear? Now we know that sigma y is 2068.4 megapascal, and this stress is very high because we use spring steel. They're very hard steel, and their use are much higher than the normally available material like mild steel, and that's why they're called spring steels, and they are expensive than the mild steel. So sigma allowable is 2068.4 divided by 3. So two zero 2068.4 divided by 3. You get a value of 689. You get a value of 689.5 megapascal. Clear? And for tau allowable, by using a maximum shear stress theory, this must be 689.5 divided by 2, which is 344.7 megapascal. So allowable shear stress in this spring is 344.7 megapascal. So if I use the stress formula, and again I am repeating, okay, the stress formula is, we know, is 8FD, and because problem it is written, you have to use the curvature effect. So FD over pi d cube 4c minus 1 over 4c minus 4 plus 0.615 divided by c. Now in the problem, neither we have a knowledge of capital D nor we have a problem of small d or c. So there are probably two unknowns and there is no information about these two unknowns. The one way of doing it is to replace this capital D by small d. The one way of doing it is to replace this capital D by small d as we have done before. So we can first calculate this factor. Okay, C is also not known. Okay, this will become a slightly complicated problem because if you have to also replace C by now this almost become insoluble. Why? Because C then become equals to D over D, and then you have to divide it by D over D, and because now you know the relation between D and small d, you have to put the capital D by small d, and it become very complicated. So in those certain problem, there is another way of finding the wire diameter, and that is very helpful in the exam if you are unable to find, because if I replace capital D by this value in all these values, like here C and all these things, this becomes so complicated that you will neither able to get small d out of this equation. So other way of doing it is considering torsion in wire. So see, as we are doing in the theory, that there is a central load and there is a torsion in the wire, spring wire, and the torsion is actually equals to tau over r is equals to T over J. If you remember, this tau is tau allowable of the spring material, r is the diameter of wire, T is the torque experienced by the wire, which is F into mean diameter divided by 2. Clear? And the J is pi by 32 D4. So if you do not able to solve it, you consider a spring wire and try to find the values from this wire. So this tau allowable is 344.7 into 10 to the power 6. The wire diameter is not known, just write d by 2. Cf, the force experienced by each, now we are talking about one spring, each spring experienced about 4.8 kilonewton, which is 4.8 into 10 to the power 3 into capital D. Now capital D can be replaced with this, 0.0. Again, please remember the units, because if you got one unit wrong, everything goes wrong. 0.025 minus D. So 0.025 minus D divided by 2 divided by pi by 32 and D. So this can be written by this cube. If I take this D cube here and take everything on the right hand side, I have to use a calculator for that. So if I take d cube on the left hand side, so this will become 32 into So this 32 actually goes in the numerator. This actually goes in denominator on the right hand side, and this d cube actually goes here, and 2 goes upward, which again multiplied with the denominator. 32 into 4.8 into 10 power 3 divided by uh, 2 into pi, because 2 is taken numerator and then goes to the denominator. 2 into pi into 344.7 into 10 to power 6. 32 into 4.8 minus power 3. Okay, so d cube become equals to, I think, 0.00071 with this 2 here also. So 2 must be so it's numerator, it's 32 into 4.8, just write 4800 divided by, okay, it's equals to, d cube equals to 0.00035 into 0.025 minus t. Clear? So if I just use multiplied in the on the right hand side, you get d cube is equals to into 0.025, which is 0.0000088 minus 0.00035d. Clear? Now some of you might be comfortable with the units of meter because diameter is so small, generally small, like 3, 4, 5 millimeter. So these values are very, very small. So if you are confused with these are very small values, go back to the original 25, 2.5 centimeter. Okay. So go back to the millimeter. You can also go in millimeters as well. No problem at all. So okay. Okay. Just checking again, there might be some error in calculations. 2 so d cube plus 0.000035d minus 0.00000088 equals to 0. Clear? Now you again, this is the either you can use a synthetic deviant for that, or you can use the hit and trial method. Clear? So you can take any value just to give an idea that ultimately the answer must be equals to 0. If you are able to do that, that will be your wire diameter. Clear? So just take a, let's say take a value of 5. Let's say d is equals to 5 mm or 0.005. Clear? So now for 0.005 power cube plus 0.00035 into 0.005 minus 0.0000088. See, your answer has become minus. Okay? You might be confused in the very small unit, I must say. Clear? So if I go back and just use millimeters rather than meters, just for your sake, that I might be have a feeling that given a very small values, you might get confused with this cubic equation. So let's say leave here and just write it again. Now with the units of millimeters and millimeters. So shear stress is 344.7. This is d by 2. T is F into d by 2, where F is 4.8 into 10 to power 3, because we are using newtons. The d is 25 minus d divided by 2. Again, now I'm using the millimeter units. Divided by, and j is pi by 32 t4. Clear? Now I'm using the units. So d cube is equals to, now if this 2 goes here and this 2 goes up, so d cube will be equals to, just write it again so there will be no confusion at all. So 32 into 4.8 into 10 to power 3 into 25 minus t divided by 4 into 344.7 into pi. This is d cube. So if I just solve now, 32 into 4.8 into 1000, which is 10 to the power 3, divided by 4 into 344.7 into pi. See, this value come out to be d cube equals to 35.46 into 25 minus t. So d cube is equals to 35.46, 25 minus d, So d cube is equals to 35.46 into 25, which is 886.5. 886.5 minus 35.46d. So d cube plus 35.46d minus 886.5 equals to 0. See, in both equations we have only the problem of, see, it is 35.46 is 0.00035. It's 886.5, it's 0.000088. So only difference is these values. But I've got a feeling, that's why I'm calculating again, that might be a confusing in the meter units because meters are very large units. Now we take a value of, let's say, let d is equals to 5 millimeter and see if the equation goes to 0 or not. So 5 power 3 is 125 plus 35.46 into 5 minus 886.5. So you get a value of minus 584.2, which is way lower than 0, which means this value is lower than this value. This indicates that 5 is a smaller value. You take it, d is equal to 7 mm. See, if this value becomes positive, way positive, which means d is value, you are taking a d larger value of small d. If this whole equation is less than 0, you are considering a lower value of d. Now I am taking the d as 7. So 7 cube plus 35.46 into 7 minus 886.5. Still I am getting the value of minus 295.28. It again means you should have to increase. This value is again smaller. Take d is equals to 8 mm now. So 8 power 3 plus 35.46 into 8 plus 881.6. Sorry, minus 881.6. Now my answer is minus 85. It means I am now very close to 0, but not 0. So just take it just for this value. You can also, in the exam you can take d is equals to 8 mm. Just take 8.2 mm, let's say. What will happen now? 8.2 power 3 plus 35.46 into 8.2. Now minus 886.5. Now I'm getting minus 44. Okay, if I take 8.5, let's say, that's 8.5 power 3 plus 35.46 into 8.5 minus 886.5. So answer is plus 29. So I've taken a larger value. See, so if I take 8 equal to 8.3 mm. In exam you can stack up with 8 as well. Just I've got a time here, so I can feel a minus of minus 20, which is good enough. So let's take it, d is equals to 8.3 mm. Now when this is known, now see, we have used a different approach for that. Rather than using a stress formula directly from a spring, we have used only the torsion in the spring wire, because we know from our theory that spring wire also experience torsion. This is one of the case if you are not getting some value, or you are actually become worried that you not get any calculate from this stress formula, then you can use this tension, the torsional shear stress formula, and then find the wire diameter. So if I find the wire diameter, now we have used the shear stress formula, which is 8fd over pi d cube into 4c minus 1 over 4c minus 4 plus 0.615 divided by c. Okay, before using this formula, we know that mean diameter is outer diameter smallest small diameters, outer diameter is 25. Now the wire diameter is 8.3. Okay, in the solution I have taken it as 8.4. I think it's good enough to take 8.42. Why? Because if I put the value of 8.4 in the, just calculate again, just for a second, I'm again repeating exam. Even you take 8, it's fine. Just for the sake that I've also solved it for this value, just take this value. What will happen to 8.4? 35.46 into 8.4 plus 886.1. So you get, sorry, minus 886. Get a value of 4, which is very close. So just take, in my case I'm taking 8.4. You can take 8, you can take 8.1, you can take 8.2. Just try to go towards as close as possible. So we are trying to go as close to 0 as possible. If you do not able to do this, try to solve it in your calculator. You can use a cubic equation, in which there will be probably this written as dq plus 35.46, sorry, plus 0d square plus 35.46d minus 886.5 d0 equals to 0. You either use synthetic division, or you can actually find the value of d. Clear? So now we know 8.4 here. So this value will come out to be 16.6 mm. Clear? So now we know value of d. So c will come out to be 16.6 over 8.4. Spring index here is approximately 2. Now that might be a problem, because you know that this will be between 3 and 21. For this problem, we might have to redesign or reconsider the spring, or probably use the bigger diameter, or you can say we have to increase the constraint condition, which is this condition. But now we are going towards with 2 as well. But generally, I'm saying in the exam, it must be greater than, it will be probably between 3 and 21. Clear? So let's continue with the problem. So tau allowable is equals to 8fd over pi d cube 4c minus 1 over 4c minus 4 plus 0.615 divided by c. So now, okay, now this is known. Why we are using this formula? Now we are now checking that whether our wire diameter works or not. Clear? And which one is a larger, we will use that. That is again very important. See, if we have calculated the wire diameter by considering a wire as a torsion, simple wire which experiences torsion. Now, because on this assumption we have find the wire diameter, we have find the mean diameter. Now we have to, now I'm now using calculating this this wire diameter from this formula, just to check again. Probably, and just I'm just focusing on this point, that when wire is converted into a spring, there is an additional stress, and this formula, you can calculate D from this formula to see when this converted into a spring what will happen. Either the D will become same, that is 8.4, or become larger. So dq is actually equals to 8fd over pi tau allowable into 4c minus 1 over 4c minus 4 plus 0.615 divided by c. So 8 into force is 4.8 into 10 to the power 3. Now I'm using the millimeter units just for your convenience. So this is 16.6 divided by pi. Tau allowable is 344.7, I think. Yes. So it's 344. That is 4 into 2 minus 1 divided by 4 into 2 minus 4 plus 0.615 divided by 2. See, the D will come out to be, and we type D prime, that will be 10.4 mm. This indicates that when you convert a straight wire which experiences torsion into a spring, the stress will be slightly larger, and now you have to a larger diameter. Now for those cases you have to use a larger diameter. The design diameter will be larger diameter. Now again find the mean diameter based on this diameter, that is 25 minus 10.4, which is now 14.6 mm. And your C prime, which is your new spring index, will be 14.6 divided by 10.4, approximately equals to 1.4. It's a very small spring index for these kinds of spring, and as told you that if, although in exam this is the spring index will be in the range, if it is not in the range, you can just write a comment that how we can increase it. You do not have to recalculate in your exam, but you can comment that how to increase it. Like in simple way, in this case, if we increase the outer diameter, probably the spring index will increase. So this is the one argument you can write in your exams. Okay. If it is clear to you till now, so we have designed three things, and I'm again repeating. Now in the first we don't know about capital D, we don't know about small d, we don't know about C, small d, capital D and C. So what we have to do first, I have to consider wire and just provide torsion in it, because even wire in spring experiences torsion. So from this I have found out the small d, the capital D. Now I have to check whether the values are compatible when this wire is converted into a spring or not. Now then I've used a stress formula to again find the wire diameter. And what I find out is that wire diameter is slightly larger than my previous assumption. Now I have to use a larger wire diameter. And now with our larger wire diameter, I have again calculated the mean diameter and spring index. Now D is known, capital D is known, and C is known. Now next thing is the number of turns. So number of turns can be found from the deflection formula. And again I'm repeating, this is the prime value and new values, and this is the active number of turns. So N will be equals to y d4g divided by eight f d okay. This is so okay. Deflection in each spring as is written in the problem is 0.9 mm in each spring. So we can using one spring for that, and so this is clearance deflection is 0.9 mm. 0.9, the wire diameter is 10.4 power 4. The G is model rigidity is 79289.3 megapascal. So megapascal Newton per millimeter square. Just write 79289.3. 289.3 divided by 8 into total load on each spring is 4.8 times to power 3, and d cube is 14 point, what we find out, it's 14.6 power cube. So when we calculate all these values, when you put all these values here, what we get is number of turns is approximately 6.98. 7 turns. This is 7 active turns. ठीक है? So total number of turns will be equals to capital N plus 2, where the spring are considered as and spring are considered grounded. So 7 plus 2, we have total 9 turns. Now the free length is N, which is total number of turns written as N prime times the wire diameter plus the deflection, and plus, now it is the clash clearance is given. Clash clearance means the total clash clearance must be 6 mm. Okay? So rather than putting the value of the 0.15 of Y max, we just put the value of 6. So this must be the clash clearance between springs. Clear? So that value will come out to be this is 9 into the small diameter is 10.4 plus deflection is 0.9 plus 6. Sorry. Again I am calculating it. Number of turns are 9. This is 10.4 plus 0.9 is the maximum deflection, which is again a very small value. If you look back to it, go back to the problem, the corresponding deflection each spring is 0.9 mm. Yes, it's a very small deflection, so it's a very hard springs. So plus 6, so get the value of just hold on, 9 into 10.4 plus 0.9 plus 6. Yes, it's 100 point. So free length is 100.5 mm. If in the exam it is not, the clash clearance is not known, so just replace this value by 0.15 of Y. At least 50% of clash clearance. Clear? Of the total deflection. So if, because it's in problem it is clearly defined the clash clearance is 6 mm, I have directly put 6 rather than 0.15. Okay. So the okay. So the pitch of the spring is free length divided by number of turns minus 1. So free length is 100.6 0.5, and this is 9 minus 1. So we get a value of approximately 100 divided by 8, 12.56. 12.56 mm. This is the pitch of the spring. And finally, if it is used to calculate K, then you will find it. Just additionally calculating. If it is, if you have to find K, then in the problem it's clearly known, clearly mentioned. If in the problem is not mentioned, I'm just calculating it for the understand. So GD4 over 8 D cube N. Yeah. If I put all these values, if G is known, D is known, these are cube new whatever. So the spring stiffness will come out to be 4139.5 Newton per meter. Sorry, millimeter. Which is 4139.5. Clear? So this is the value we have actually calculated from this. So this is the one problem that if we give an idea how to solve the problem, I will upload another problem with the solution, and this is very similar problem, that problem related to the valve springs in IC engines. They also use helical spring, helical compression spring. But just for the sake of just understanding, I will upload another problem for the um, for your practice. Now, thank you very much for your time. In the next part of this lecture, we are going to solve um, we understand the theory of leaf spring, and then we solve one or two problems related to the leaf spring. Thank you very much for your time. Allah Hafiz.